Okay, good morning, everyone. So the second morning session is about to start now, and we are going to begin with a talk by Professor Mathias Klaui, who has been a leading expert in spintronics ever since his days as PhD student working with Tony Bland at University of Cambridge. After that, he has held appointments at IBM Zurich, Constance, Lausanne, and for last more than a decade by now, he has been based at University of Mainz. And today he's going to talk about this. His talk will be another talk on manipulation of Skyrmion, but he'll approach it from different angles. He will talk about how we can use orbital angular momentum of electrons to manipulate Skyrmion. Okay, let's give him a big hand, and this is going to be a great talk.
Okay, no pressure. Thank you very much. Thank you very much. Well, thanks, Akbom. Also, thanks, TIC1 and the PCS Institute for hosting this exciting workshop. So I've already had some talks, and we heard the last talk already about Skyrmions by a colleague from Seoul National University, Professor Kim. So yeah, today I want to go not just about Skyrmions and how to make Skyrmions, how to stabilize them, but also how to use them for low power GreenIT applications. And I'm going to cover essentially 5 topics. So I'm going to look at topologically stabilized Skyrmions, then how to manipulate them using Spin-Orbitronics approach to looking at Skyrmion dynamics, and then actually use this type of Skyrmion dynamics for non-conventional logic using Skyrmions, and then finally summarize. So before I start, let me very briefly introduce Mainz. Mainz is conveniently located in the center of Europe. We're closest university to Frankfurt Airport. And we have a beautiful old city. And also we are the home of the first data revolution. And the reason is that Johannes Gutenberg is the hometown of Johannes Gutenberg, who is the inventor of the printing press using movable letter type. And in the 16th century, the idea of not just copying the book by hand, but actually using printing press had exponential increase of the amount of data available. And he's also the namesake of my university, which is a leading research university with a strong focus on physics and materials. So if we look at how data has evolved, we find that up until about 1993 or so, the vast majority of all data has been in analog storage. Books, video, microfiche, and so on. And between 2000, where 75% of data was stored analog, and 2007, where 90% of data was stored digital, something happened. And the question is, why suddenly everyone switched from analog to digital? Now, if you ask, there are many suggestions like invention of some, GMR hard drives or something like that. And technology has something to do with it. But there's something more banal in it. And that is, if you look at the price of dollars per megabyte, then this has been continuously going down, both for disk drives and semiconductor. And if you look how much it costs to store information in paper and film, you see it's about 10 cents. And around this time, it simply became cheaper to store information digital than to store information analog. And that's something that I learned at my time at IBM. In the end, you would like to have always cheap solution, not only good solution. So we need both. So since now it's cheaper to store information digitally, we can use it. And we can use it, for instance, for the development of new memory. And we all know the Racetrack device, which was suggested and first developed by Stuart Parkin. But there's also magnetic logic and, of course, magnetic sensors. And in all these applications, what we need is we need to have stable information, and we need to be able to manipulate information with low power. So first, in order to store information, we want to explore special Skyrmions. Let me introduce how we can stabilize Skyrmions and what they are. Now, everyone knows that typical in magnetism, we have Heisenberg exchange, which stabilizes two parallel spins parallel or anti-parallel. However, the spin-spin Heisenberg exchange interaction does not stabilize skyrmions with a certain topology, but it stabilizes simply spins with all kinds of directions as long as they are parallel. Now, this is a problem because if you have states that have different topology and different chirality, then there are many decay channels and this reduces the stability. So we would like to have, in addition, some exchange interaction which stabilizes certain states with fixed chirality or fixed topology. And you can see, for instance, here two examples of domain walls which have different chirality. This domain wall here, when you go from left to right, you can see that the spins are rotating clockwise. And here, if you go from left to right, the spins are rotating counterclockwise. Now, we would like to have some interaction which stabilizes only this domain wall, but not this one. Unfortunately, nature actually has something for us in store, and this is the Dzyaloshinski-Moriya interaction. Now, this interaction couples two spins, M1 and M2, not just parallel due to Heisenberg exchange, but additionally due to the orbit of an atom in a heavy metal layer adjacent to our magnetic material, such as platinum. Also, a stabilization of the two spins with a 90-degree angle, so cross product. And even better, we not just stabilize 90-degree angle, but only this and not this. So there's only this and not the other orientation. And this means if you now combine Heisenberg, which wants parallel alignment, and Dzyaloshinski-Moriya, which wants perpendicular alignment with a fixed chirality, you see that going from left to right, the spins now always rotate in a clockwise fashion. And that means if we now have a domain wall like this one here, we can see that when the magnetization rotates clockwise, as shown here, this is energetically favorable. By this domain wall here, where now the spins rotate counterclockwise, this is now energetically unfavorable. And so this combination of highest domain walls with fixed chirality. And if you increase the interaction even further, you can stabilize these Skyrmions, which I will explain later. But first, let's understand how this Dzyaloshinski-Moriya interaction can enhance stability. To do this, to check this out, what we do is the following experiment. We have here a multi-domain state with chiral domain walls. And we now do a small angle X-ray scattering experiment at the Fermi free electron laser, where we get this typical ring here. And this ring is simply the sum of circular left and circular right polarized light. And it corresponds to the width of the domains. So here, this Q vector is 2 pi over the width of the domains. And the intensity of this ring is a measure of the collinear order of the magnetization in the domains. And if we shake it, and the whole thing starts a bit shaking, then from the intensity of this ring, we can see how good magnetic order is in the domains. Now, in addition to the sum of circular left and circular right, we can also look at the difference between circular left and circular right. And this difference here is now a measure of the chirality of our domain wall. And from the intensity, this red-blue, we can get the degree of ordering of our domain wall. If it's perfectly red and blue, it means that all domain walls are perfectly. And if you shake it again and the domain walls become unstable, then this contrast, red and blue, will go away. So now what we can do is we can measure the intrinsic intensity of this ring, as well as this contrast, to quantify the amount of order, the collinear order of the domains, and chiral order of the domain walls. And now we see that before the laser, we use the laser pulse to actually make the domains and the domain walls shake and reduce the ordering. Then the laser pulse has hit, the order of the domains has gone down, and it goes down even further, and then it recovers. And if we look at the chiral order of the domain walls, then we see that the chiral order of the domain walls also is reduced. That first, the collinear order, as well as the chiral order are reduced due to laser irradiation. But then when we look at the recovery, we see that the chiral order of the domain walls recovers more quickly than the collinear order of the domains. And this means that chiral order is more stable than collinear order. So if you shake the system by irradiation with laser pulse or heating, then first chiral domain wall forms and then later domains form. And that means chiral domain wall is more stable. Okay, so now if we increase the DMI, we can stabilize Skyrmion. So what is a Skyrmion? Here's a lot of interesting papers about Skyrmion. For us, Skyrmion simply is a spin structure which is confined geometrically, where we can map the domain, this spin structure onto the unit sphere. So we see here the domain, the spins at the outside of the Skyrmion are mapped onto the North Pole, and the magnetization at the center of the Skyrmion is mapped onto the South Pole. And then somewhere in between, the magnetization has to rotate, and you get such a chiral structure as shown here. Now, this typically can be a metastable state or a ground state, and you can characterize this spin structure by a topological winding number, which is given by this. And the topological winding number for this spin structure here is n equals 1. For this spin structure here, it's also n equals 1. And that means you can, by continuous deformation, you can convert this spin structure into this spin structure. It's easy to see how. For instance, this spin here will rotate up, this spin here will rotate left, and so on. And so that in the end, you have here such a spin structure which can be continuously deformed between these two, or also between this one here. What is also important is that this topology of n equals 1 is distinct from the uniformly magnetized state where all the spins are parallel. So if you want to destroy this spin structure, you have to change the topology. And this is, for instance, different from this spin structure here, which we call bubble Skyrmion, which has Skyrmion winding number n equals 0. And that is the same as the uniformly magnetized state. And so this means that this spin structure here can be continuously deformed into the uniformly magnetized state. So without changing the topology, we can destroy the spin structure. And this means it has low stability. And I can show you also how. So if you apply a small field to destroy the Skyrmion, this Skyrmion here will simply shrink a little bit, but be stable. But this Skyrmion here, with just a little bit of field, it can continuously rotate to annihilate, and therefore we completely annihilate the spin structure, forming the uniformly magnetized state without changing topology. So that's the importance of topology. So n equals 1 is topologically stabilized or topologically protected spin structure, because in order to create a uniform state and annihilate the Skyrmion, we have to overcome the energy of Bloch point formation, which is high energy. Whereas this one, the n equals 0, we can continuously deform to the uniformly magnetized state. Now we can simulate this, and when we do this, we find that to actually, of course, there is no infinite topological protection, because in a continuous description, there is, of course, this protection, but in real life, life is discrete. We can always form a Bloch point to annihilate the Skyrmion, but there is a strong energy barrier, and to model that, we need to correct, lattice constant. And for a continuous model, if you shrink the Skyrmion to 0 size, even then, there is no strict topological protection. Now, if you're interested, we recently published this paper here, where we looked at the stability in a lot of detail. By the way, if you're interested, I'm also happy to share the slides. So experimentally, many Skyrmions have been found. So I just give you a little bit of an overview that Skyrmion spin structures have been observed in multi-layers made of heavy metals such as platinum or tantalum or iridium, and ferromagnets such as cobalt, cobalt, boron, cobalt, platinum, and so on and so on. Now, Skyrmions have been found in sizes ranging from a nanometer, a couple of nanometers, to micrometers, as shown here, and they all have the same topology, which is important. So they share a lot of common features, such as their dynamics. Now, if you're new to the field, here are some reviews where you can read up. And I'd just like to point out that for thin film skyrmions, there was some first observations, for instance, in this paper here by Axel Hoffmann's group, and then also our work here, as well as people in Grenoble and Paris. Now, in addition to these metal systems, more recently, we also looked at insulators. Now, insulators are very interesting because potentially magnetic insulators can have very low power dissipation because there's no moving electrons. And for instance, in thulium-ion garnet, strong spin-orbitox have been reported. And so we measured the Dzyaloshinski-Moriya interaction and found that we actually have strong Dzyaloshinski-Moriya interaction with a very long decay length. And this allows us to stabilize skyrmions in this magnetic insulator. Furthermore, we can also very efficiently manipulate these using orbital torques as shown in this paper, and I'll come to this topic of orbital torques later. So now we have skyrmions in metals and in insulators, and these are 2D skyrmions where the thickness of the layer maybe is 1 nanometer, but the size of the skyrmions is hundreds of nanometers. But we can even have 3D skyrmion spin structures. Now here is a comparison of the typical Dzyaloshinski-Moriya interaction as shown here, where we have a canting of the spins in the plane of the ferromagnetic layer due to different interaction with the two non-magnetic layers above and below. But you can also couple two spins in two ferromagnetic layers, like in a synthetic antiferromagnet. And if the lateral translation symmetry is broken, we can also induce a chiral coupling, leading to not just parallel or anti-parallel, but also to a canting between the spins in the two layers. And this can stabilize three-dimensional spin structures, such as this one shown here. And this interaction was first found by two groups, our group as well as the group of Fernandez, Pacheco, Russell, Coburn in this paper, which was published actually head-to-head, back-to-back. Now, why are we interested in these 3D spin structures, as is this one shown here? Because fundamentally, 3D spin structures could be very exciting for applications in storage and 3D storage. But also, if we look at non-conventional computing like our brain, in our brain, every neuron is connected by 10,000 or so synapses to other neurons. Now, if you want to connect in 2D, then the problem is that in 2D, you can only on average connect to 4 neighbors. That's graph theory. If you don't have like crossings, which is difficult to realize. So if you want to connect one neuron to 10,000 other neurons, the only way to do that is in 3D. And so potentially with these 3D spin structures, one could also obtain the huge interconnectivity of our neurons. So that's why I think it's very exciting. All right, good. So now we have stable skyrmions in 2D and 3D in metals and insulators. Now let's manipulate them using spin-orbitox. Now, I already explained to you that, of course, we have the standard spin-orbit torques, and these spin-orbit torques can be generated by the spin-Hal effect. Here's a review by Hyro, where essentially a longitudinal charge current leads to a transverse spin current, or in a structure as shown here, you see a longitudinal charge current means that all the spin right electrons are scattered to the top interface, and then they diffuse into the ferromagnet and manipulate the magnetization. There's a second effect for electrons flowing at the interface, the Inverse Spin Galvanic effect, or the Rashba Edelstein effect, where essentially Rashba coupling generates a non-equilibrium spin density at the interface that by exchange interaction also acts on the magnetization, and thereby it can manipulate the magnetization. So this is the spin-Hal and spin galvanic effect, or spin Rashba Edelstein effect, but more recently also the orbital Hal effect has been predicted, as in this paper here, which essentially is also a longitudinal charge current, which is now converted into a lateral orbital current. Now, this is very interesting because it was predicted that these orbital Hal currents, can be orders of magnitude larger than the spin Hal currents. So potentially, you can generate much larger orbital Hal currents. And if you can then convert them to spin currents, you can very efficiently manipulate the magnetization. And there's also the analogon of the Rashba Edelstein effect, which is the orbital Rashba Edelstein effect, where at the interface you generate a non-equilibrium orbital angular momentum density. So this was described here in this paper here. Now, I'm not going to go into a lot of detail, but essentially we observed both the orbital Hall effect as well as the orbital Rashba Edelstein effect in these two papers here. If you're interested, have a look. And I'm also very happy to share the slides. Now, we want to use these effects now to manipulate magnetization, and in particular to manipulate skyrmions. So here is some early work that we did a few years ago, where a student, a Korean student, Seung-Hoon Woo, he drew this very nice picture of a Skyrmion racetrack, where he put the skyrmions into our nanowire and then inject currents to move 4 skyrmions back and forth. Now we then did, or he then did the experiment, and we started with these 4 skyrmions here and injected current, and yes, it works. Well, if you look closely, you see, yeah, it does work, it moves, but we initially, in the beginning, we start with 5 skyrmions, and after a few displacements back and forth, we lost half of our data. Only 3 skyrmions are left. So that's not very good. And if you talk to Samsung or Intel, they're not interested in a memory that loses half the data. So the question is, what is happening? Now, we did some theory, and in theory, everything is perfect. So we have 3 skyrmions, which are moved by the current to the left or to the right, depending on the current direction. And they all move on the same trajectory as shown here. And they actually don't move exactly in the direction of the applied current, but under some angle, the so-called Skyrmion Hal Angle. Now, in the experiment, we have one skyrmion, the yellow skyrmion, which does what we expect. We have another skyrmion, the black skyrmion, which doesn't do anything. And then we have the red or the orange skyrmion, which actually eats the black skyrmion. And this shouldn't happen because there's topological protection. But you can actually see here that there are 2 skyrmions which are playing Pac-Man. So one skyrmion is actually chasing the other skyrmion and is then annihilating with the other skyrmion. Is not working. And the question is why? Now, if you look closely, you can see that the first skyrmion eats the pinned skyrmion. And we find that only when the skyrmions are pinned, they can actually annihilate. If the skyrmions are moving freely, they play billiards, they bounce off each other. But if they're pinned, they can actually annihilate. And so we need to find out where this pinning comes from. And to do that, and this is some work which was actually published last week, so it's the first time I show this, to check the origin of the pinning, we actually made an experiment where we actually get a pinning landscape of a device. So here in this device, what we do is we have skyrmions which are actually moving around, and we measure where they get pinned and how long it takes the thermal excitation to move them out of the pinning site. And we find that, you see, there are some positions like the dark red ones where the skyrmions stay a long time. So they're very strong pinning sites. And there are also some dark blue areas where the skyrmion never goes. And this means this is an energy hill. So it's an energy maximum where the skyrmion never goes to. And so what we can do is from this, we can actually quantify the skyrmion energy landscape. And here you can really see the skyrmion energy landscape, so the pinning landscape in this device. And in our case here, the skyrmion pinning strength is of the order of the thermal energy here, so that actually the pinning at these positions is sometimes a few seconds, sometimes a few minutes, sometimes a few milliseconds. But the question is why and how is it pinned? There have been a lot of reports where people modeled the pinning simply by actually fixing the center of the skyrmion at a certain position. But then we zoom in and we see the following behavior. Now here you can see the skyrmion which is moving around. And when it is moving around, it's not actually moving as a whole to any position, but you see it likes to stay in certain positions. And when we now image the skyrmions in 4 different positions, and in black, you always see the surrounding of the skyrmion. So that's the perimeter of the skyrmion. And here in red, you see the skyrmion when it's put this position. In green, we see the skyrmion when it's at this position. In blue, we see when the skyrmion is at this position. Then what we find is that the skyrmion domain wall very often actually is pinned at a certain position. And it's not the center that is pinned, but actually it's the domain wall that is pinned. We can actually see this, that even when we have striped domains, the domain wall of the striped domains is pinned at the same position as the domain wall of the skyrmions. So really what we can see here is that the Skyrmion boundary domain wall is that governs the pinning and not the center of the Skyrmion. And this is also something that is easy to understand because actually the Skyrmion domain wall is the most highly energetic part of the Skyrmion, and therefore if the Skyrmion can lower its energy by pinning the domain wall at a position where the DMI is different or the exchange is lower, then this of course will lead to strong pinning. So the important information here is that the pinning occurs at the domain wall. And now to reduce the pinning, what you want to do is you want to get rid of, for instance, grain boundaries, because grain boundaries pin Skyrmions. So then we went from the typical platinum, cobalt, tantalum layers to layers which comprise amorphous cobalt iron boron. And in this cobalt iron boron stacks, we actually find that we can move the Skyrmions very reliably. And here the student actually did 50 motions of the Skyrmions, and you see they can all move back and forth without being annihilated. But then if you talk to Samsung or Intel, they are not happy with 50 motions. They want actually something of the order of 10 billion motions. And you cannot do that by just clicking every time on the pulse generator, but you can go to a synchrotron and do a pump probe measurement, where here we see a movie, and this is the movie of 10 billion repetitions of moving Skyrmions back and forth. And we see it's fully reproducible, because if only once the Skyrmion would have gotten stuck, then we would not see this black-white contrast, but just gray. Furthermore, we see that the current here is flowing under an angle with respect to the Skyrmion motion direction, and the Skyrmion velocity tracks the pulse shape very nicely. So if we now have the current flow right-left, the Skyrmion moves, or the 5 Skyrmions move at this angle here, the Skyrmion Hal Angle. And this was predicted to depend on the size of the Skyrmion as well as its topology. However, it was predicted that the Skyrmion Hal Angle should be independent of the Skyrmion velocity, but this is not what we find. We, and actually also our colleagues from the group of Axel Hoffmann, we found independently that the Skyrmion velocity actually influences the Skyrmion Hal Angle. That meant that the current understanding, theoretical understanding, using a rigid Skyrmion model is incomplete, and we need new theory. So then we teamed up with some theoreticians, and also had a lot of discussions with the colleagues, the Reichards from Los Alamos. And then it was found out, and we published this paper here, that the theory that they put forward first was based on creep, is applicable in the low speed creep regime, whereas our explanation was applicable in the viscous flow regime, and that is based on deformation of the Skyrmion spin structure. So overall, there is a change of the Skyrmion Hal Angle with velocity, and there are different origins. I mean, meantime, there are a number of nice papers that actually explain this. All right, so now we have Skyrmions you can move reliably, speed back and forth as for this, for instance, Skyrion Racetrack. Now, the next thing that we wanted to look at is diffusive dynamics due to thermal excitations for lower power applications, because if you look at the application of strong current pulses, this of course is very power intensive. So what we did is we looked at this stack here, which is was similarly proposed in this paper here. And then we find that the Skyrmions, when we inject current pulses, they move along the current direction at the Skyrmion Hal Angle, but also we see that they wobble around. They're not only moving to the left, but they're also moving up and down, and this is some thermal excited motion. And this was actually first predicted in this paper here, Christoph Schutter, but it was actually predicted to be suppressed. And so therefore we wanted to check, is this real diffusive Skyrmion motion? And to do that, I told the students, well, just switch off the applied currents and switch off the fields and just image the direction of the motion of the Skyrmions. And here we see Skyrmions which are being moved at zero current, so there's just thermal excitation, no other excitation. We see they randomly move around. And actually here we can use a machine learning in order to track the positions of our Skyrmions. So we can then plot the trajectories in the mean square displacement, and we find that the mean square displacement is completely linear in time, and this means it's really pure diffusion. This was also reproduced by atomistic spin dynamics simulations by the group of Oli Novak, and we published this jointly in this paper here, and later also some colleagues found similar results. Now, it was then actually, and that's how I got into the business, it was then actually predicted that such thermal Skyrmion motion could be used in stochastic and reservoir computing. And so that's what motivated me to go into this field. One of the things that you need, however, if you want to use these for some of the non-conventional computing approaches, is you need to control the dynamics of the Skyrmions. And in order to actually control, at least partly, the diffusive dynamics, what we did, we applied in-plane fields. Now, at zero in-plane field, the Skyrmion is round. And if it is round, there is no difference in the diffusion up, down, or left, right. So x and y. So the mean square displacement along x and y is the same. But if we apply, for instance, 2 millitesla in the x-axis, then what we see is the Skyrmion gets elongated, becomes elliptical, and also there is a strongly anisotropic diffusion. You can actually see here it moves more left-right than it moves up-down. We see we can have 50% higher direction if you apply a field. And this, for instance, could be useful for token-based Brownian computing, as I'll explain in a minute. And we've looked at this in this paper here if you're interested. Okay, so now in the last part, and one of the more important parts here is I want to show you some possible applications of Skyrmions for non-conventional logic. So one of the things that I learned in the discussion with companies is don't try to beat a company list like Intel or Samsung at what they're good at. For instance, Boolean logic. Don't try to make a better AND or OR gate because Intel is pretty good at making AND or OR gates. So one approach that we're going to start with is stochastic computing. So let me explain to you stochastic computing and then how we can use Skyrmions for that. Now, stochastic computing is a non-arithmetic way of calculation using random bit streams. It's actually an approximative approach with progressive precision. I'll explain what this means. And it's good only for certain tasks. For instance, it's good for multiplying numbers if you just employ AND gates. And the problem is the creation of unbiased, uncorrelated bit streams. And this is what we want to solve using Skyrmions. And I'll explain this in a minute. And by the way, I should explain that this was put forward in this paper by Daniele Pinabel. So firstly, how do we represent information in stochastic computing? Now, if you have a coin and you flip a coin, then it's 50% heads and 50% tails. And this is the probability of heads is 50%. Now, if you have 4 cards, and then the probability of drawing an ace is 25%. And this information of 50% or 0.5 is actually encoded in a bit stream, which comprises the same number of zeros and the same number of ones. So 50% zeros, 50% ones. Now, the information of 0.25, 25%, is encoded in a bit stream that comprises 25% ones and 75% zeros. And now what we can do is we can actually use our bit stream, which corresponds to 0.5, and our bit stream that corresponds to 0.25. And we can feed these two bit streams into an AND gate. Then 0 and 0 is 0, 1 and 0 is 0, 0, 0 is 0, 0, 0 is 0, 1 and 1 is 1, and so on. And now it turns out that if this resulting bit stream, which you get from this AND gate, that this resulting bit stream is actually simply the multiplication of our two numbers A and B. So the bit stream from the AND gate is simply 0.5 times 0.25, so 0.125. So this is a way by just feeding our two bit streams into an AND gate to multiply the two numbers. And with these bit streams, we can represent any number between 0 and 1, so any number that we want in the end. However, the result of this AND gate leading to the multiplication is only correct if the bit streams X and Y are uncorrelated. And so let me explain what this means. Now, suppose we feed in the bit stream which corresponds to the value 6 or exactly the correct result. Now, if we put in 2 bit streams, which are completely correlated, then we see here 6/8 times 6/8, and we have a completely correlated bit stream. We also get 6/8, and that's obviously wrong, because 3/4 times 3/4 is not 3/4. So what we need is, we need to decorrelate the bit streams here by reshuffling the numbers of ones and zeros, but keeping the total amount of ones and zeros the same, because we still need 75% ones and 25% zeros, but not anymore in this order. So maybe we should have, instead of 1, 1, 0, 1, and so on, we should have 0, 1, 0, 1, or whatever. In the end, the important thing is that the total amount of ones and zeros stays the same, but the order is shifted around. And this we tried to actually implement by a reshuffler. So here's our reshuffler. Now the reshuffler makes use of our thermal excitation. And here we have the skyrmions, which are produced here, which is the input stream. When they cross this blue line here, it's an input 1. And when the skyrmion crosses the blue line here, it's an input 0. And then we have here the reshuffler chamber. And then when the skyrmion crosses the red line here, it's an output skyrmion, output logic 1. And if it skyrmion crosses the red line here, it's an output logic 0. So now let's do this. So we see here, the first skyrmion entered here was a 0. Now a skyrmion entered here, it's a 1. Another skyrmion entered here, it's a 0. Now the first skyrmion exited here, it's a 0. Now another skyrmion exits here, it's a 0. Now a skyrmion will exit here, it's a 1, and so on and so on. And so here's our input stream, and here's our output stream. And now what you can already see is that the skyrmions in these 2 reshuffler chambers, they don't just straight move through, but they actually, by thermal excitation, they move a little bit up and down. So the time that a skyrmion takes to get from here to here is actually not deterministic, but actually has a certain amount of probabilistic nature, and therefore the input and the output stream look different, but because every skyrmion that enters here also eventually exits here, in the long run, the number of ones and zeros stays the same, just the order has shifted. And we can quantify this, and we find that the p-value, which is the numbers of ones and zeros, stays exactly the same. So this means not a single skyrmion has gotten lost, and that's because we have this topological stabilization. But the correlation is down to 11% between the input and the output stream. So this is really good, because it means that we can now generate decorrelated bit streams as necessary for stochastic logic. And this was actually tried to make cover page of Nature Nanotechnology, and we obviously failed, but I still want to show you. This is our mixer, our skyrmion mixer, our reshuffler. And now we can combine our skyrmion reshuffler with an AND gate, as suggested in this paper here, and thereby we can actually multiply numbers using probabilistic computing with very low power. So that's the first approach for which we need these topological spin structures, these skyrmions. Now we come to the second approach. And the second approach that I wanted to explore is token-based Brownian computing. So again, I'm going to first introduce the general concept and then show how we use skyrmions for that. So token-based Brownian logic that relies on tokens, which are discrete signal carriers, which in our case are skyrmions, but that can also be other objects, can even be mice or something like that. And then it comprises a circuit which has certain special transition rules. And for instance, here we have a token with 2 inputs, 1 and 0, and here token, 2 inputs. So if the token is up here, it's a 1. If the token here, then the input A is a 0. If the token here, then the input B is a 1. And if the token is here, the input B is a 0. And then we feed, for instance, here the 1 and the 0 into our circuit, and then they do something, and then we get a certain output. And this was actually developed a long time ago. And an overview article is a nice overview article is actually shown here. And what we need in order to realize this special circuit is we need 3 entities, which is a hub, a ratchet, and a C-joint. So let me explain what this is. A hub is simply a connector between different wires or interconnects, where the skyrmion, when it goes in here, has a choice to go right or left. a ratchet. Well, it's a ratchet, so skyrmions can only go up, but not back down. And the most important is the C-join. The C-join actually means that if two skyrmions arrive at the same time at this position here, then they enter at these two from these two directions and they exit at two different directions. If only one skyrmion arrives here, then it cannot go through, but it goes back where it came from. Only if two skyrmions arrive together here, they can actually exit and go to these new directions. And this is where the computation is done. So the hub was already implemented in this nice paper here by our colleagues from Yoshiki Suzuki's group. And the C-join was also suggested experimentally in this group here. And so here is an example of a possible logic circuit. And this possible logic circuit actually is a so-called half adder. So here we now look at the thermally excited calculation of this half adder, and we feed in a 0, 0. So the input A is 0 and the input B is 0. Okay, and here we go. So now the skyrmions, they move randomly back and forth, and at some stage they meet here at the C-join. And when they meet at the C-join, they exit through the new path, and then eventually they move to the output. And so there's a carry bit and the output bit, and you get 0, 0. So 0 and 0, 0. Okay, good. So this works. However, it has some problems. And that is you actually have here some crossing lines, which is not so ideal. And furthermore, one of the biggest problems of this approach is that it can take a long time. So we actually developed, firstly, a crossing-free geometry. And this actually allows us to already significantly improve the speed. So here, for typical thermal diffusion of skyrmions, we have a few minutes of calculation for the traditional circuit. But in our crossing-free circuit, we're already 4 times faster. And additionally, if we have induced dynamics, we can get orders of magnitude faster calculation. So we go from minutes to microseconds. And if you're interested, the results are here in this paper. Here we also filed a patent. Now, finally, let me show you what I find is a very exciting approach, which is reservoir computing. Now, reservoir computing is similar to neural networks, where we want to map a complex problem to a linearly solvable one. And by the way, I should acknowledge here Karin Everschor-Sitte, from which some of these slides are provided. So you have a reservoir. A reservoir is a complex non-linear entity where you feed in some information from an input and you read out some information to an output. And the important thing is that in this reservoir computing, the reservoir is essentially an interconnected recursive neural network, which, however, we do not train or do anything to it. The only thing that we train are the weights for the input and the output. And so this network, the reservoir itself, does not need any tuning, but only the output connections are tuned. Respectively, the input somehow needs to be, the output is trained, and the input, of course, also needs to be tuned. And this reservoir computing thus is very, very efficient because the training calculation needs are very low. And what it does is that the reservoir projects different spatial temporal events into a sparsely populated high-dimensional space where we can easily categorize them because of these hyperplanes, which allow us to easily find, for instance, categories or actually detect certain things. Now, this was first suggested in this paper here by Pchenenko, Karin Everschor-Sitte, George Buryanov, and myself, that we could use skyrmion fabrics as a reservoir, having inputs where we, for instance, locally inject currents, and having outputs, which could, for instance, could be TMR junctions that detect the resistance, and from the resistance, the magnetization below, so the skyrmions below. So here we actually have an input that is encoded as currents here and an output which is then measured as a resistance, and then we can use this, for instance, for the detection. Now, what we did is we actually implemented a simple version of that experimentally in this paper here, where we have a triangle. And in this triangle, we have 3 contacts. And these 3 contacts can each have 3 different input values, namely positive voltage, negative voltage, or 0 voltage. And with that, we can then actually drive currents through our triangle. And this driving of the currents through the triangle will then move the skyrmions in different positions. And these different positions can be read out locally, for instance, by TMR junctions. And then we can use this to detect information from or to learn information that we feed in through the input. So the input in our case is actually currents. And you see an example. For instance, in this example here, we have thermally excited skyrmions, but on top, we have a very low current. Actually, it's 3 to 4 orders of magnitude smaller than what is typically used for racetrack type of dynamics. And we push the skyrmion with this current here towards the bottom left. Here we have the current flowing from here to here. We push the skyrmion towards the bottom right. And now there's a very strongly nonlinear process because of the edge repulsion of the skyrmion. And also a big advantage is that when we switch off the current, automatically the skyrmion, due to the edge repulsion, will always go back to the center. And then we read out these 4 positions here by mimicking TMR readout using the Kerr microscope. And this allows us to actually obtain the standard Boolean operations as a proof of concept. Now, for each combination of inputs, AB, the output Q is shown for a set of local skyrmion occurrence probabilities. So light blue is always our training, and black is the set that we use for testing. And we see here, for if we train for the AND gate and we put in 0, 0, then we get as the output 0. If it's 0, 1, we get output 0, 1, 0, we get output 0, but 1, 1, we get output 1. And what is important is that we can even obtain non-separable functions such as XNOR, which you could not actually get with a standard perceptron. So here the XNOR, we see 0, 0 is 1, 0, 1 is 0, 1, 0, 0, and 1, 1 is 1 again. So this is kind of nice because this means that we already, with our very, very simple reservoir computing approach, we can outperform a simple perceptron. And now we're in the process of also extending this to time multiplexing, which was suggested in this paper here, and which we are just working on, for instance, for gesture recognitions. Okay, now the most important slide here is the people that did it. So in particular, I'd like to acknowledge Gerd Jakob, Martin Jordan, Hartmut Zabel, and Peter Werner, permanent staff scientist and our research professor in the group. This is what we looked like before Corona. This is what we looked at during Corona. And now we look more like this again, which is great. We also have very good collaborations. The early work was started with the group of Jeff Beach, theory with Oli Novak's group, also experiments with Peter Fischer, and numerical simulations with Jonathan Lilliard, Bartel van Weinberge. Imaging was done at the PSI with Simone Finizio, as well as Bessie with Markus Weigand. Also, we work with a group of Gisela Schütz, Hermann Stollen-Förster at Max Planck Institute in Stuttgart, and we have a lot of very good theory collaborations with theoreticians in Mainz, Helen Gomonai, Peter Werner, Daniela Pina, Karina Everschor-Sitte, Juromir Krusov, the 3D Magic ERC grant consortium, Stefan Blügel, Rafael Bakowski, Theo Rasing, Johann Menting, and Christian Gutt, as well as theory people from Sendai and Sydney. Nothing would work without the funding, so in particular, I acknowledge the ERC grant. And so with that, I summarize. So the DMI stabilizes chiral spin structures with defined topology, and we've identified that the pinning happens at the domain walls of the skyrmions. The skyrmion motion due to spin-orbit torques leads to Skyrmion Hal Angle, which has multiple origins. And thermally induced anisotropic and isotropic diffusion can be used for probabilistic logic, but also token-based Brownian computing and reservoir computing. If you're new to the field, here are 2 reviews or 3 reviews, which I invite you to read. If you're interested in the slides, send me an email. And with I put the email address in the chat. And with that, I thank you for your attention. And I'm looking forward to the questions. Thanks.
Okay, I think we still have time for a couple of questions. So please raise your hand if you have any questions. Okay, let's start with second.
Yeah, thanks for the nice talk, Mathias. So if you compare this probabilistic computing to quantum computing, in quantum computing industry, now people can do solve some problems that that is very hard to solve with the classical computers, right? With the large of qubits.
Yeah.
How long do you expect to be able to solve that kind of very hard problem with this probabilistic computing?
I think it's a very important question. My take on this is that there are certain problems for which a quantum computer is really good. Certain optimization problems, RSA, cryptography problems, but there are many problems for which a quantum computer is not very efficient because there are no good quantum algorithms. So certain detection problems, for instance, pattern recognition, certain machine learning approaches, for which also Boolean logic is not very good, but for that, certain of the non-conventional computing approaches are very good. So my view is in the future, we will have a computer which is going to use for standard calculations Boolean logic, for certain pattern recognition is going to use non-conventional computing, such as neuromorphic, and for certain tasks, such as optimization, it's going to use a quantum computing approach. So I think we will need all these approaches. I think there's no single computing paradigm that can solve everything fast and with low power.
Yeah. How long do you expect?
Well, I think machine learning is already there. Now the question is, hardware implementations of machine learning are being very actively developed because they could potentially really outperform in terms of power consumption the standard, let's say, TensorFlow units using Boolean logic by orders of magnitude. So I don't know, I'm not a company, but I am pretty sure that in the next 10 years, we will have hardware solutions for non-conventional computing that will be implemented in computing centers.
Okay, yeah, thanks.
But don't quote me on that. But it's very exciting science. Yeah.
Okay, next question.
So, hello.
Yes. Hi.
Yes.
So I have a very simple question. So you mentioned that in your initial slides that this there is a data showing the calculation of Dzyaloshinskii-Moriya interaction, the strength and measurable, measured one with the experiment. How do you measure it experimentally? This strength of Dzyaloshinskii-Moriya interaction?
There are different ways. So one is you can measure the asymmetric spin wave dispersion relation because Skyrmions moving left and right will have different energy for same k vector. Another option is you can measure a domain wall motion because if you have Dzyaloshinskii-Moriya interaction, you will favor Néel walls, and by applying in-plane fields, you can tune between Néel and Bloch wall, and you can measure that. You can directly image the domain wall spin structure. So there are a range of different approaches that you can use depending on the system and your availability of certain measurement equipment in the lab. If you send me an email, I'm happy to send you a slide where I have an overview of all the different methods of how to measure it.
Okay, sure, I will do that. And maybe a small question again. So these Skyrmions, so is it, I don't know, maybe I'm wrong, but is it correct to think of some sorts of lifetime when you drive the current up to that they will survive, and then they will not survive? So there is some kind of lifetime. So up to that they will move coherently and then they will decay or something. So is there a time scale to think of that?
So as with everything, there is a finite lifetime, but the Skyrmions can be made 40, 50, 60 kBT, so you can make them stable over 100 years if you want to. But you can, of course, also, there are Skyrmions, very small Skyrmions, which maybe have only energy barriers of a few kBT, which only live milliseconds to seconds. So that depends really on the magnetic properties, the volume, and so on. So you can tune the stability of the Skyrmions from ultra short to ultra long, depending on your application.
Okay. Thanks a lot. Yeah, thank you.
Okay, so let us thanks Matthias again for his wonderful talk.
Okay, thanks a lot for the invitation.